Okay, so this is section 8.4. It's our last, basically, usually our last topic of the course. And this is something called the normal approximation of the binomial distribution. What this means is the binomial distribution, if you look at it, especially if you look at it for a large amount of outcomes or a large sample size, it actually starts to look almost exactly like the normal curve. Now, remember that the binomial distribution is discrete. So that when I look at this, it's a discrete variable, random variable x. And remember, the binomial distribution was a discrete probability distribution, but it also looked at multiple trials viewed as success and fail. Okay, so if you remember that, you can view something as a success and a fail, and you do quite a few trials of it. In fact, for most of these, you need to do a fair amount of trials of them for this to actually work. But as the trial size goes up, the binomial distribution of probability starts to kind of look more or less like the normal distribution. Now, it can be skewed one way or the other. Generally, a perfect skew, a perfect normal distribution for a binomial distribution, where the two of them marry together really nicely, happens when the probability of success and a fail are roughly the same, or 0.5 each. In that case, you can actually do it for a very, 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 very small sample size. But as you move on and on and on upwards and further away for probabilities from 0.5 for a P and a Q, or for a success and a fail, then you can still use this normal distribution and the normal approximation of the binomial distribution. Reason being is a couple of things. So as we go through this sort of set of examples, you'll also be able to explore when it's pertinent and when it works and when it doesn't work. So what I'm going to do for both of these is I'm going to do a normal approximation to the binomial distribution, that trick that we use, and then I'm going to use, of course, just the binomial distribution in order to calculate, because you can always use the binomial distribution to do it. It just may be a little bit cumbersome. Okay, so a discrete binomial distribution can be approximated with a continuous normal distribution as long as NP and NQ are both greater than 5. So this is a rule that's in place. If the number of trials times the probability of success and the number of trials times the probability of failure is not both bigger than 5, you can't use this. It's too dissimilar. It's not going to approximate it correctly. Okay, so it's like a little checklist you have to go through before you can even do it. Okay, often the binomial distribution calculation is simplest. It's the easiest to do. So you can go ahead and do the binomial distribution calculation like we did in section 7.2 of our discrete probability distributions section. But if the sample size gets large, okay, a normal approximation may take you less time. Okay, and as a result, then it's a better way to do it. Okay, and it has to meet a couple of criteria. A couple of things if you're going to do that. Remember that if you're going to do a normal distribution question, you need to have mu and you need to have sigma. Well, you have a mechanism to figure what mu and sigma is. Mu is the number of trials times the probability of success. And sigma, or standard deviation, is the number of trials times the probability of success times the probability of failure, the square root of that value. Okay, so here's the situation. This is a binomial distribution situation. Suppose that 65% of the families own computers. If 30 families were surveyed at random, okay, so my sample size is pretty big. My n is equal to 30, okay. What we're going to do is we're going to look at the different ways we can do this. One, we're going to use the binomial distribution calculation, and the other one we're going to use the normal approximation. The normal approximation takes a little bit more work. So first what we're going to do is we're going to do the binomial distribution on this side. And I've got a nice, beautiful note done for you guys, so you can follow along with that if you want to as well. My n is 30. My probability of success is 65% own computers. It's the A asks what's the probability that 20 families own computers, or P at X equals 20 successes out of the 30. Okay, my P is a success, which is 0.65. Again, multiple trials, 30 families are sampled. A success, 65%. A failure is 35%. And I know that it's a binomial distribution because I'm taking it from a large sample size, or I'm assuming I'm taking it from a large sample size. So the probability of success or fail stays the same. Okay, and so it's again an independent event, multiple trials, looking for a specific number of successes. So how would I do that? Well, X, what I'm looking for is 20. And so what's P at X is equal to 20, or what's the probability of having 20 successes out of 30 trials? Okay, if you remember how it's all built and put together, we have, first of all, success, 0.65, and that happens 20 times. And then we have failures, And because we do a total of 30 trials, 10 of those would have to be non-computer owners. Okay. Now, the number of ways in which this could arrange itself as I was interviewing the 30 people has to do with the choose. And the choose, of course, is going to be 30, a number of trials, choose 20. Okay, the number of successes. All right. Now, this is going to end up being a bit of an awkward number. Okay. 30 choose 20 is 300,45015. I'm just cheating. I would normally use my calculator for that. And then this is, 0.0001 dot dot dot. And then 0.000, and then that's the whole idea. You keep it all in your calculator. If you kept it all in your calculator, you get 0.1502. Okay, and that's the probability. So therefore, prob of 20 people of 30 own a computer is 0.1502, or about 15%. Okay, and that's the probability of that happening. Okay, sampling 20 people and getting, of course, 20 who have, sampling 30 people and getting 20 who have computers. Now, for the normal approximation, we're going to use the normal distribution. So it's going to be a normal distribution question. But in order to do that, remember, we have to have a mean and we have to have a standard deviation. My mean is NP. I also have to do NP and NQ to make sure that they're both bigger than 5. Well, NP is going to be 20, that's my sample size, times P, 0.65, which is 19.5. And then NQ is going to be, we have to make sure that's also 5, although it's not going to help us with any of our calculations, 0.35, which is going to be 10.5. Okay, so if they're both greater than 5, okay, then we know that we can use this, the normal approximation to the binomial distribution. My sigma, remember, is going to be the root of n times p times q, or the root of, well, if I calculate that, I don't have that calculation done here for me, but if I calculate the square root of 20 times 0.65 times 0.35, I end up getting 2.6. So my mean is 2.6, my standard deviation, my mean is 19.5, my standard deviation is 2.6. So I want to find out the probability that x is equal to 20. Same thing. Okay, remember that if we're going to do, okay, so here's my mean at 19.5. We're going to have 20, which is going to be right beside it here. So it's going to be this bar that is represented by 20. So remember the bar of 20 goes from 20.5 to 19.5. Okay, and we want to know this area in here. That's the probability that x is equal to 20. Already you know that we're having to do way more work for the normal approximation than we are for the binomial distribution, in which case for an equals, it's almost always better to do a binomial distribution, unless you can't, and that has to do with the choose calculation. All right, but anyway, so we've got p at x is equal to 20. How do we get p at x is equal to 20? Remember, that's the probability of being between 19.5 and 20.5. Right, remember I'm figuring out the area under the curve. It's a normal distribution question. Area under the curve between 19.5 and 20.5. That's a probability of x is equal to 20. Okay, and then of course I can't do this sort of a scenario. I have to turn it into less thans. So remember that's the probability of the big, probability x is less than or equal to the big, minus the probability that x is less than the small. They're both less than, so I can do that. Then I do z-scores for those. Okay, a z-score for 19.5. It's going to be an easy calculation. 19.5 is my barrier minus my mean, 19.5, all over my standard deviation, 2.6, which of course is just 0. So that's a 0.00. And then 20.5 is going to be 20.5. That's my barrier minus my mean, 19.5, all over 2.6, which comes out to be 0.38, of course, rounded. Okay, 0.38. So then I look up those values. That's 0.6480 minus 0.5000. and we end up with 0.1480. Now that and that are pretty darn close to each other. Okay, so therefore, the probability of having 20 people owning a computer using the normal approximation is good, and it's an approximation. It's close. I mean, it's off by about 0.2%. Okay, so it's a small percentage, 1/5 of 1%. Okay, but there you have it. Now, in this situation here, what's the probability that 20 families or less own computers? Okay, so I'm going to do a binomial distribution. I'm going to do the normal approximation. So here, what's the probability that x is going to be 20 families or less? So x is less than or equal to 20, which is going to be probability of x is equal to 0, plus the probability of x is equal to 1, plus ... plus the probability of x is equal to 19, plus the probability of x is equal to 20. That's going to be a lot of calculations. It's going to be 21 calculations. Or if you're clever, you go, oh, well, no. That means that it's 1 minus the probability of x being 21, plus the probability of x being 22, all the way up to the probability of x being 30. Either way, that's a whole heck of a lot of calculations. 10 calculations, 10 calculations, and then subtracting it from 1. Too much work to do. I'm not even going to bother. I mean, I can do it. I'm not going to do it. Okay, too lazy. I'm going to use my normal approximation. So here I want p and x is going to be less than 20 families or less than or equal to 20. Okay, so I draw my normal curve, draw it a little smaller this time. Draw my 20 barrier. Now remember, the barrier is a bar. It's always going to be a bar when you're using the binomial distribution because it's the discrete probability distribution. So 20 goes from 19.5 to 20.5. We want less than. We know we want less than, so it's going to be this part, right? But the big question is, do I include the bar or not? 20 families or less. That means I include the width of the bar, and so I go to the barrier that's on the right-hand side. So this is a less than, and it's the barrier on the right-hand side. So my continuous correction is going to be less than or equal to 20.5 rather than using the 19.5. And that's what I want. I want this from this area over. I want all of it, okay? Now the beauty is it's a less than. If it's a less than, then I don't have to turn in anything else. For greater than, it's 1 minus the less than. For in-betweens, it's the big minus the small, both of them less than. In this case, I can go straight to the z-score for 20.5, and then I get a probability. So the z-score for 20.5, this is something familiar. We've already done it already. 20.5 minus 19.5 all over 2.6. We've already calculated all this. We've already made sure that it's okay to do all of this. So we're branching forward from that. Otherwise, we would have to figure out NP and NQ, make sure they're both bigger than 5. We'd have to figure out what mu is, which is NP. We'd have to figure out what sigma is, which is the square root of n times p times q. Okay? But we don't need to do that here. Okay, and as a result, all that work's already done for us. So we know this is 0.38. 0.38, and it's 0.6480. Now in this case, the normal approximation, super easy question to do. It's a very small space. I was able to do this here. Imagine how many of these calculations I would have to do for that. I'd either have to do 21 of them and add them all up, or I'd have to go 1 minus and take from 21 all the way to 30, do those 10 calculations, add them all up, subtract them from 1, and then get my answer. And I'd still get the same result or very close to the same result. So this is a pretty good way to do it. Even though, 65% for a success and 35% for a failure, it's a very good approximation. And as my sample size gets bigger, it gets more and more accurate. Okay, so that's how we do the normal approximation to the binomial distribution. And this is a situation where it's much more useful for us. In the next situation, part C, what I have is kind of the same idea as the 20 families or less own computers, but in this case, what's the probability that 25 families or more own computers? Now, in this case, how would I do 25 or more? I could do 25, p of x is equal to 25, 26, 27, 28, 29, and 30. Okay, and I could do those 6 calculations using the binomial distribution. I'm not going to do that. I'm going to use the normal approximation. It's a little bit quicker for me to do. Again, you'd have to do, if you're doing this from scratch, you'd have to figure out NP and NQ, Make sure that they're both bigger than 5. In this case, we've already done that, right? Remember, this comes out to 19.5, and this comes out to 10.5. They're both bigger than 5, so check. I know I can use the normal approximation. And then I would want to know what sigma is, which is the square root of NPQ. And again, that comes out to 2.6. So there's my mean. And so when you're doing the check, you're calculating your mean anyway. My standard deviation is there. It's the same thing that we've been doing all the way along for all this example because I've been keeping it the same. The probability that 25 families or more own computers. So probability 25 or more. X is going to be 25, or it's going to be greater than. 25 or more means greater than or equal to. So I draw my bar at 25. I'm going to draw a fat one there. Okay, there's 25. That means 25 goes from 24.5 to 25.5, and I want to know 25 or more. So or more is this part right here. And then because it's 25 or more, it means I include the bar because I include the 25. So that means the barrier that I go to is actually all the way through to the 24.5. And I'm including the left-hand side barrier that I'm going to use. So that's my barrier. So my continuous correction is going to be, instead of p at x is greater than 25, it's p at x is going to be greater than or equal to 24.5. Okay, now I can't do a greater than, remember, for the normal distribution. So what do I have to do? Well, greater than is 1 minus the less than version with the same barrier. Okay, same thing. Okay, it's a greater than is 1 minus less than. Less thans I can figure out z-scores for, and less thans I can actually do values for. There's also a trick for your z-score for greater thans, but I'm not going to show you that. I'm going to let you figure that out on your own, or maybe a tutor can help you with that or something like that. I've got to figure out what the z-score is for 24.5, so z is going to be 24.5 minus 19.5 all over 2.6. That's going to be 5 all over 2.6, which ends up being, let me consult my trusty answer key. 1 second. 1.92. So my z-score is going to be 1.92. Of course, positive. It's above the mean of 19.5. And I go ahead and I look at my trusty z-score table, just as I've been doing all the way along. 1.92, 1.9, all the way over to 2, 0.9726. And so I go 0.9726. And so what is the probability of having 25 or more families out of the 30 owning computers? Okay, and that's quite simply 0.0274. So therefore, the probability that 25 of 30 own computers is about 2.74%. Okay, fairly unlikely. Now, the normal approximation of the binomial distribution, very, 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 very useful. Okay, even more useful when things start to get really, really big and sample sizes start to get really, really big. There's a couple of things that happen as you go onwards with this. As it says here, in summary, steps B and C are way easier to use the normal approximation to the binomial distribution. Ease is certainly an important feature, but you're actually going to get to the point where you can no longer use the binomial theorem anymore. And that's when your choose calculation just gets to be too big with a conventional calculator. Now, if you use Microsoft Excel, it'll keep quite a few decimal places, and it can raise things to the power of above times 10 to the 99. Okay, so it's able to do that type of a calculation for you. But still, the idea is that once sample sizes get really big, even if P and Q are really far apart from each other, it becomes much, much better, much, much easier for you to use the normal approximation to the binomial distribution. Okay, and so I've got some homework questions here for you. It's quite a few homework questions to do, but you do need to practice this. It's also a great way for you to practice. You only need a couple of questions for using a continuous distribution to solve discrete variables. Okay, or applying the normal distribution to discrete variable conditions. Okay, so as a result, it'll give you more practice with that. So hopefully that's fairly clear to you. You definitely need to know how to do the 3 sections beforehand, or at least the normal distribution, and then applying the continuous distribution to discrete variables. But either way, once you get those down pat, this is a pretty easy process to go through. Okay, so try those homework questions and go from there.